So there's a fair number of new terms here that we just want to become familiar with, and these are ways of describing aspects of graphs that we'll see throughout this course. I think one of the best ways is just looking at this. So I have a graph here of 3 to the negative x times 5x minus 3 minus 8x squared, but where the domain is restricted to just values that are greater than or equal to negative 0.5. And while I will go to Desmos, for the most part, everything we need is here. And so just in terms of labeling some things, first I want to mention our turning points. Turning points are where the shape of your function turns, but it turns from increasing to decreasing or decreasing to increasing. So for example, this, and this are all turning points. And there's a few other things we can label about them, but I'll start with that. For example, the vertex of a quadratic function is a turning point. All right. Another term I want us to be familiar with is what we call the global maximum or the global minimum, which just means the highest possible point on a graph if we're visualizing it as a two-dimensional graph, or what really means is the greatest possible output. And keep in mind, not all functions have a single greatest number that comes out of it. In this case, this does. It's the highest point, which I can see this same point that I'll now highlight in blue as well. This point here shows the highest point on this graph. And so besides being a turning point, we can also call this a global maximum. It's the highest single point of the entire function. And similarly, we have a global minimum, which is this point down here. That is the lowest possible point. This is where, in this case, it's where this function also begins or ends, depending how you want to look at it. But that's the lowest point. And so I'll label that as the global minimum. All right, we also have local minimums and local maximums. And those are the highest or lowest points in their region. And so, for example, if I look at this point here that I'm going to underline in purple or circle in purple, this point here, in its region, it's the highest point. Now, it's not the highest point overall, but in its little region, it's the highest point. And turning points are always also either local maximums or local minimums. And so this point here, it's not the highest everywhere, but is the highest in its little neighborhood around it. So we also call this a local maximum. And I can say something similar for this point right here. It's the lowest point in its little region, and so we can call that a local minimum. The last term I want us to be familiar with here is what we call an asymptote, and there's two types of asymptotes. There's horizontal asymptotes and there's vertical asymptotes, or I should say there's two types of asymptotes that we'll be looking at in this lesson. And it's a little hard to tell immediately until we're familiar with these sort of characteristics, is that this function has a horizontal asymptote on the x-axis. And it's a little more obvious, and it's easy for me to explain if I switch to Desmos because I can zoom in on it. So here is the same function in Desmos. And if I look at this function and I go along to the right, it seems to get right on the x-axis. And if I zoom out, it clearly doesn't go below the x-axis. However, upon inspection, you'll see it never actually reaches the x-axis. As it goes on, and it goes on forever, it gets infinitely close, but it never actually reaches the x-axis. It gets progressively closer and closer without ever actually reaching it. And so anytime that happens horizontally at some point, because you can see it's, for all intents and purposes, this now appears like a horizontal line. It's not, but it sure appears like one at first. And so this is a characteristic we notice when we have what we call a horizontal asymptote. And a horizontal asymptote is a feature we draw on a graph quite often to show what I've just described, in this case, something in which the graph never actually touches the x-axis, but it gets infinitely close to it. And so in Desmos, I can see everything I need, but on paper, we generally we show it with quite often a dashed horizontal or vertical line. And so I'm going to show it with a dashed orange line, in this case, right along the x-axis. This just shows that this graph has a horizontal asymptote on the x-axis, or where y equals 0. So horizontal asymptote at y equals 0 in this case. Because keep in mind, the x-axis is the same as a horizontal line where y equals 0. And so this symbol is just showing, particularly this region over here, that even though it may look like it's touched the x-axis, it may look like the y-coordinate has equaled 0. It actually never does. All right, so a good number of perhaps new terms kind of described here. Let's look at this, where I want to sketch the graph of just f of x, 1 over x squared minus 1, and I want to include the equation of any asymptotes, as well as classify any extrema. And again, extrema are global maximums, local maximums, and all that sort of good stuff. And so first, well, let me graph this function here, because again, we're always encouraged to use graphing technology. And so here's a nice graph of it already. And if I just look at this graph, I can get the general sort of shape. Notice there are a number of asymptotes here. There's a horizontal asymptote on the x-axis again. And if I zoom out, again, it's similar to before. This time it goes both the left and the right. It looks like it touches the x-axis. It looks like a horizontal line along the x-axis, but it's not. And if you zoom in, you'll notice it gets close, but it'll never actually reach the x-axis. However, there's also vertical asymptotes here. In this case, where x and y equal minus 1. And if I zoom out, it sure looks like they're going straight up and down. It sure looks like they reach negative and minus 1, but they never actually do. And I can zoom in and see it never quite reaches those points. And all this makes complete sense if we look at the equation. The equation was x squared minus 1 in my denominator. And keep in mind, when x equals 1 or negative 1, my denominator will equal 0. And remember, you can't divide by 0, but you can divide by numbers very, very close to 0. And which is, this is why we're seeing these vertical asymptotes in this graph. Because essentially what I just said, you can divide by numbers extremely close to 0, but actual division by 0 is undefined. And so my graph gets extremely close to 0, infinitely close, but never actually reaches, in this case, when x is negative 1 or 1. My function is not defined. And so let's start the process of sketching this out. I'm going to make a quick little XY axis here. Keep in mind, when you're asked to sketch a graph, you don't have to draw it to scale, but this is a fairly easy one to kind of sketch out. And so I'm going to label some key points, where there was a vertical asymptote at negative 1 and a vertical asymptote at positive 1. I'm actually going to draw those right now. If we draw the asymptotes before we sketch our function, it gives us a structure to work around. I generally recommend always sketching your asymptotes first once we know where they are. And remember, there's also one on the x-axis, so I'll sketch that right now. And when asked for the equations of these asymptotes, the horizontal asymptote, again, is on the x-axis, or I can say where y equals 0. The two vertical asymptotes are where x equals negative 1 and where x equals positive 1. Those are the equations of them. Now, in terms of some other details from the graph, if I zoom in a bit, I can see this point at 0, 1, which is a local maximum in its little region. It's definitely not the global maximum. I'll talk about that because it's not the highest point in the whole graph, but in its area it is. And so let me sketch and label that point there. So at negative 1, I got something like this. I should draw these arrows. And so that point there, like I've stated, it is a local maximum. That's it. The only other characteristic I need to sketch from this graph, there are no x-intercepts. Generally, we want to show those when we're sketching, but just I can see the shape on either side of these asymptotes, and I'll just sketch it like this. Remember, it doesn't go through the asymptote, so I'll just kind of get close to it, show those arrows, good enough. All right, that's my graph of f of x. Keep in mind a few other things I can label. That local maximum is also a turning point. All local maximums and local minimums are also turning points. In terms of global maximums and global minimums, this function does not have one. There is no highest point. It goes up forever. It goes down forever. So this function has no global maximum and no global minimum. There's many functions that don't have them, that don't actually have a highest single point anywhere, or lowest single point. All right, I think I've accomplished everything the question is asked there. Here's the last one. I got G and H, it really should say. Mind my typo. there we go. So I have function g and function h. G is a linear function, h is the 7th degree polynomial, we say. Determine the number of points of intersection between the graphs, and does h of x have any asymptotes? So I don't have to sketch anything here. But first I want to visualize these functions. Now 20x plus 1, function g, very simple linear function. Function h, not as simple, but fairly quick to type in. And when you graph this, you should see something like this. I'll go back to my basic zoom settings. Here we go. Now, the function in this case in black is h, the polynomial of 7th degree. The function in purple is the line. And so upon first glance, it looks like there's one, if I zoom out a bit, it looks like there's one intersection. There's definitely one intersection point right there. However, keep in mind, we quite often have to think about our window settings. And if I just zoom out, or even better on here, if I just kind of compress my scales of my y-axis, there we go, I can see there are indeed a total of 3 intersection points here, here, and here. And so the question didn't ask for the actual coordinates of these intersection points, so I'm just going to say there are 3 intersection points. And always got to be wary when you first graph something with your basic zoom settings. It's really easy to lose sight of the fact that it's hard to immediately know what happens outside your window settings. In this case, if I just zoom out even just a little bit, I know I have a line in purple, and the line goes at the same slope always. I know I have this 7th degree polynomial, and so there must, without even actually zooming out, I know there must be an intersection point down here because the purple line doesn't stop, and there must be an intersection point up here because the purple line doesn't stop. Either way, in the end, there are 3 intersection points here. Lastly, does h of x have any asymptotes? Well, no. Although you could be fooled into thinking there are. In fact, let me get rid of g of x for a moment and show you f again. If I look at function f, there were these 2 vertical asymptotes. Function f, remember, being from the previous question. These parts in which it looks like the graph is going perfectly vertical, it never does. In the case of function f, the one in green, it never quite reaches x values of 1 and -1. However, while you may think this is similar, you may think there's a vertical asymptote close to -2 or a +2. Keep in mind, h of x is a polynomial. X can be any number, which means the domain is all real numbers, which means this graph can't have any breaks in it because there's no reason there'd be any breaks, which means there can't be an asymptote. Asymptotes happen when a function gets infinitely close to a point. And a vertical asymptote is when you have some x value that you can get really close to but quite can't reach. And so there can't be any asymptotes here. You can also, if you not so much zoom out but adjust the scale, notice as I keep compressing my y scale, my graph never actually, it just keeps going more to the left and the right. There's no limit. It's not reaching some point where it breaks apart. Whereas if I do something similar with f of x, if I compress my y scale, notice it's not making a difference in terms of where those asymptotes are. This function is clearly having this break. And so h of x has no asymptotes. Polynomial functions never have asymptotes on their own. And so that's pretty simple. The last part, the answer is nope. Nope. No asymptotes of any kind.